Bismillah. Seek ye first the kingdom of God and all of his righteousness. Again, my name is Mr. Sharia. My contact information is researchpublishingmedia@gmail.com. This is in association with Dr. Tutor. We're Zoom available. We're speaking about math analysis. Math so difficult. It makes life easy. Now, we were speaking about my brother, Minister Eric Muhammad. He's down in Atlanta, Muhammad Temple number 15. For us, as black people in America, the nation of Judah, to gather up under that brother and listen to what he's saying to get us organized, to get up out of this hellfire that we are in, that we are living in. Okay. So then I wanted to speak about, we have put this problem on the board. Okay, we speak about math analysis. We said that 1 plus 1 equals 2. We have to prove this statement to be true. We want to prove that 1 plus 1 is 2. So we began to take steps to prove it, right? So the first thing we talked about was an inequality. So when you talk about an inequality, or when you speak about math analysis, you're talking about symbols. It's the language. How do you use the language to communicate mathematics? So it's symbols. So you got the plus symbol, you got the equality symbol, you even got the numerical symbols. It's just symbols, and you have to learn that language. So we started with the inequality, right? And we also said that we were dealing with the natural number set. Remember, the natural number set, we represent the natural number set we're in. And the natural number set starts with 1, 2, 3, and it goes to infinity. The natural number set does not include 0, and it does not include fractions. And when you're speaking about fractions, we're speaking about rational numbers. I say fractions, but the correct terminology when you speak about the literature is rational numbers. Rational numbers are represented by the letter Q, the symbol Q, and you'll say Q is equal to P over S. Now the letters or the variables that you use to show that it's a fraction, remember it's a fraction, P over S or 1 over 2 or 3 over 4, it's just fractions. So we represent, well, it's not necessarily represent, well, you can say that P over S is representing 1 over 2, but it represents more than that, because again, 1 over 2, you're speaking about specific numbers. P over S is an unknown number, or unknown variables, not unknown variables. P is a variable for the unknown numbers. S is a variable for the unknown numbers. So it's a separate type of thought, where it's more analysis and creating theory. But whenever you see something like this, a variable, it could be A over B, it could be M over N. But whenever you see in the literature, when you're speaking about math analysis and you see something like M over N, well, they're talking about rational numbers. And rational numbers are represented with the letter Q. That's good because we're talking about sets. And just to give you a brief description of a set, let me see. No, we were going to hold on, but we're going to speak about sets. And okay. So we're talking about natural numbers. Again, 1 plus 1 is equal to 2. We want to prove that. So what we say is, we brought in the inequality. But before we even got into the inequality, we said that 0 is less than 1 is less than 2, plus 0 is less than 1 is less than 2. That's equal to 1 is less than 2 is less than 3. Okay, so then we said that that's putting a boundary on 1, it's putting a boundary on 1, it's putting a boundary on 2. Again, when we say 1 plus 1 equals 2, what are we saying? Like in your mind, you say you know what $1 is, correct? Or you know what $1 can purchase. It's a better way to say it. But you don't really know what 1 is. Really, you got to define what it is. If you're talking about 1 is a counting number, well, yeah, that makes a lot of sense now because you know what 1 is. 1, anything you're trying to count. But if you just say 1 plus 1, that's heavy though. Because like, even if you ain't, okay, say we not talking about nothing. And I say 1 plus 1 is 2. You see what I'm saying? Like, that's true. But what make it true? What make it true really is the symmetry between 1, 2, 3 to infinity. That's where God come in, brothers and sisters. And that's heavy. And see, we done made it all crazy, even though it's good for your brain, but like again, you know, what's really good. So that's powerful. That's powerful because I speak about something, or God showed me something like, again, what I want to work on my doctorate in. It's called number symmetry. Number symmetry. And you'll find that, like, let's look at number symmetry. How come, like, you can add numbers, 1 plus 1 equals 2, but you can add variables, A plus B equals C. And the reason why you can do that is because of the symmetry of the numbers. And when, again, we talk about symmetry, we're just talking about, initially we're going to start off with natural numbers. The symmetry of natural numbers and including 0, or whole numbers, what they call whole numbers. I'm not going to call it whole numbers until I study what the origin of whole numbers. But we're going to say the natural number set, how I want to do this. Okay, we talk about number symmetry. So listen, we're just talking about the number set. That's a good point. Number set. Not the natural number set, but just a number set. And our number set starts with 0 and it goes to infinity. We're not talking about no negative numbers. And we have to understand our foundation is natural numbers. Our foundation is natural numbers. That means that we have come into this understanding of the number set from natural numbers. We looked at natural numbers. Now, we haven't done an in-depth doctorate study on natural numbers. That's what I want to look at with this. Well, not necessarily natural numbers, but with this number symmetry, we just want to be fluent in that. But our foundation understanding is from natural numbers, from farming. I'm a farmer. And just in learning how to grow situations in the cultivation of land and dealing with the creation of God, you have a good understanding of natural numbers. So from that understanding, we're coming into something now called the number set. Not the whole number set, not the rational number set, not the real number set, not the integer set. We're talking about number set. And our number set is 0, 1, hold on one second. 0, 1, 2, 3 to infinity. Now we're not going to put the infinity symbol after these dots, but that's understood that those numbers go on to infinity. And from the number set, we want to look at the distance between 0 and 1, the distance between 1 and 2, the distance between 2 and 3. Now, again, we're not trying to get too scholarly into what I mean when I say distance. A lot of times when I say distance, you already know what I mean, right? And then so how you want to define that. But right now, before I even put language on it, we're just talking about the distance between 0 and 1. And you know what that means. At whatever level you at, even a little child, if I say, look, the distance between 0 and 1. Now, he might not necessarily, or she might not necessarily know how to articulate what that means when they see it, but they'll know what that means. So we're talking about the distance between these numbers. And that distance is exact and it's precise, right? And it's because of that precision where you have number symmetry, where you can add numbers and variables, but you see it more when you get into, when you start getting into statements, where you can add statements, but those statements okay, when you talk about like, okay, that's going to be kind of difficult, right? But yeah, when you just talk about statements, say you're trying to add, okay, say you have something like, okay, I'm going to take this off the board. You should write this down and just look at it. It's called number symmetry. So you might have, okay, we use this symbol right here. It's the parentheses. All right, when you're writing a sentence, and you might say the cat is black. And then you might put in parentheses, chapter 1, and then you put the period to end the sentence, right? So we use parentheses in that type of context just to distinguish and know it's like a separate thought. But when you talk about math analysis, we use parentheses to group. Now, it's not a group or a set, but you can use it in that language. We're just talking about initially. We use parentheses to group, to distinguish separate from what's going on. I say that because when you talk about adding statements, and you might have 1 plus 1, and then you want to add that to 3 plus 4. Or you might have 3 plus 2, and you want to multiply that times 1, or you want to multiply that to 1 plus 3. Now, I want to say this is, you learn something in mathematics called the associative property. And initially when I started putting it on the board, I wanted to use that, but we don't have to use it in this situation. So let's look at this statement right here. 1 plus 1 plus 3 plus 4. Now what the parentheses does is it lets you understand, it's a language, communication. It's telling you and me that you have to add what's in between the parentheses first. So you have to add 1 plus 1 first, 2 plus, you have to add what's in the parentheses first, 7. And then you can add these two numbers to equal 9. And that's the answer for this statement, necessarily. Right? Now, you can add 1 and 3, because when you take the parentheses down, it's just 1 plus 1 plus 3 plus 4. This is a very simple statement. So you can add 1 and 3, that's 4. Then you can add 1 and 4, that's 5. And that's equal to 9. So you get the same answer. And look now, we added the numbers up separately than how this is arranged, but we still come out with the number 9. That's where the symmetry comes in. Okay. So my whole point is that it's because of the symmetry of the number set, 0, 1, 2, 3 to infinity. Because of that symmetry, because of how God has made that thing perfect, sort of, kind of, as far as the human being, well, you can add numbers all kinds of ways. Okay. So, now, we have 0 less than 1 less than 2 plus 0 less than 1 less than 2 is equal to 1 less than 2 less than 3. So then what do we do now? Okay, so we want to put a value on these again. We don't know what 1 is, we don't know what 2 is. So we have to put a value on that. You got to define that. So we're saying that coming out of the number set, coming out of the number set, we want to have a set of natural numbers set, and remember the symbol, the union symbol. And then we want to create a set of this 0. Right? And then what variable you want to call it? Let's call it M. So we have a set M. Set M is the natural number set union with the set 0. So that'll give you 0, 1, 2, 3 to infinity, and we equate that to the letter M. Now we can put bounds on it, where it only goes, the natural number only goes to a certain number, but that's going to introduce more terminology, and I don't want to get it confused. Well, we were trying to keep it simple. Okay, so once we define the set M, we know what M is. Get it in your mind that the set M is the natural number set in union with the set 0. And that'll give you 0, 1, 2, 3 to infinity. So what I'm going to do is I'm going to take that down, and I'm just going to put M as our new set. Okay, so we have a set M, and set M defines our inequality because we're using 0, 1, 2, 3 natural numbers and the set 0. So then what do we say? Oh, this is good. This is so good, right? I love this jump. Math analysis, listen, math analysis is the thing, right? Okay, so then we said we could do this, right? We said we could do 0, 1, 2 implies, remember that symbol? It's an arrow, 2 lines with the connecting 2 lines. That symbol, when you see that symbol, that means you are implying something. You are doing this for this right here. Now, they have a technical definition, but that's so confusing. So I'm just going to give it to you how I see it, how we use it in the literature as far as writing. When you use this arrow, that means you are implying something. So when we say 0 less than 1 less than 2 implies that 1 is less than 2. And the reason why we're trying to say 1 less than 2, because look, we're trying to get this part right here. 1 less than 2 is in the answer. It's 1 less than 2 less than 3. Now again, remember what we're trying to do now. We're trying to prove that 1 plus 1 equals 2. Like you might hear that all the time, but they ain't proved it. You don't know that to be true. So let's prove it. So we first have to put a value on each one of the variables. So we say that 1 is less than 0, is less than 1 is greater than 0, less than 2. That puts a value on it, sort of, kind of, right? Because it's a whole lot of numbers before 1 gets to 0, if you're talking about real numbers. So we got to put that number set in a certain type of boundary, and we call that the number set M. which is natural numbers, or the set M, natural numbers and 0. So once we do that, we know that the value of 1 is less than 0. No. The value of 1 is greater than 0, less than 2. Oh, you got to really understand. I pray you understand that, because that's the value. You understand that? Like, that's a value. The value of this number right here, 1, is that it's greater than 0 and less than 2. So when you talk about natural numbers, there's only one number that's below 2, and that's 1. There's only one number that's greater than 0, and that's 1. So that's the value of 1. So now we have established 1 to have a value. Then we had to establish 2 to have a value. So then we say that 0 less than 1 less than 2 implies that 1 is less than 2. And the reason why we wanted to have 1 less than 2 is because we're trying to prove that these two parts of this statement is equal to this. So when you have this right here, you're a little bit closer to getting to what the hieroglyphs say now. The hieroglyphs say if you got 1 tomato, you have another tomato, that's 2 tomatoes. Or that's, if you follow the addition operation, you'll have 2 tomatoes. Okay, it's equal to 2. Well, 2 tomatoes look like this. So if you got 1 tomato and you added the 1 tomato, you'll have this right here. So 2 tomatoes, you have this right here. You bring that down, you put the equal sign. They look just alike. So using the hieroglyphs, we just proved that 1 plus 1 equals 2. So now we want to use the script. So using the script, we have to show that this side of the equality is going to be equal to this side of the equality. So now look what we done now. We done got a little bit closer to 1 less than 2 less than 3. Okay, so then when we say that 0 less than 1 less than 2 implies 1 less than 2, we have to also say that, like when you're writing, to make it make sense, we have to say that we can write this without this inequality losing its meaning. If you look at the last lecture, I couldn't really come out with a word how I wanted to say that. But we can write 1 less than 2 without this inequality losing its meaning, where the statement is still valid. That's powerful. Okay, so then how do we do it, right? We came down to, so now we say that 1 less than 2 plus 1 less than 2 is equal to 1 less than 2 less than 3. Okay, and then I couldn't go no further, right? Because I had to look at it. So it's not that we can add and subtract inequalities as far as following the arithmetic principles, but from the number system and the symmetry of the numbers, we can just freak these inequalities. This is how we do it, right? So what we have to do is this. Look at this, right? What we do now, this ain't in no textbook or nothing, but the whole thing is we just got to show that they're equal. And the way we show they're equal, I mean, if they look alike, then they're equal. Unless you're talking about something internal, that's getting way, we're not talking about that. We're just talking about, listen, 1 equals 1, 1 equals 1 initially because they just look alike. If we ain't know what none of that was, we say, well, okay, say if we only knew what the equality sign meant. We know what equal means. Well, look, without putting a value on it, without using the hieroglyphs or the script, if we say we write 1 equals 3, well, are they equal? No, they're not equal because on this level, they don't even look alike. Right? You can even say this. Now, you can say, like, once you gain control of your intelligence, you say, well, listen, we say 3 equals 1. But you got to write that, and you got to let the people know that's what it is. So if you say 3 equals 1, and then you say 1 equals 3, well, this is a true statement. Because you say over here 3 equals 1. But because 1 does not look like 3, they are not equal. Or like you can say 2, and you can say 2, and you can just draw it all crazy like, but it looked like a 2. Are they equal? No. Common sense tells you and me that they're not equal because they don't look alike. Okay, so let's look at this, right? Look at what God say, right? God say, look. God say, look. God say, bring this down. And then subtract the 1 to the side, right? So look, we say -1 plus 1 less than 2 plus 1, right? So we solve this inequality. 1 minus 1 is 0. 2 plus 1 is 3. So now we have 1 less than 2 plus 0 greater than 3, right? So then we just add them two together, right? And how we thinking? And we say 1 less than 2 less than 3. So you say, well, what happened to the 0? Well, you have to make the statement, make sense. You can't say 1 less than 2 less than 0 less than 3, because that don't make no sense. You see what I'm saying? You have to make it make sense. Let me put that up there too, right? Because a lot of times, like, you might have a thought, you don't write it down, and you don't think that's not significant. That's very significant. You have to make it make sense. You have to make it make sense. See, again, from slavery, what has been done to me and you, the crimes. Crimes. Waiting for our slave master to tell us what to do. No. So then we have to learn how to make it. You got to make it make sense. You can't wait for nobody to tell you what it is. Okay. So look, right, let's do it again. Look at how beautiful this is. Oh, this is so powerful. We got to the point where it was 1 less than 2 plus 1 less than 2 is equal to 1 less than 2 less than 3. So then we need to just add this to see if this equals this, equality. So what we do, we bring the 1 less than 2 down. So we say 1 less than 2. Then this 1 less than 2 over here, you add the 1, hold on a second. Okay, hold on 1 second. Okay, so no, that was sort of correct. Okay. Now we can't add the 1 like that, right? So if you say 0, 1, 2, no, you got to subtract that 1, right? Because that's a positive 1. No. Oh, that's terrible. Okay. This is how we can know that's still not going to be right, right? Okay. So we defined it here. What if we say, if we subtract 2 to both sides, right? We say minus 2, that'll give you -1 less than 0. So then we'll say -1 less than 1 less than 2. So then you add, right? You might could do it like that, right? So that'll be, if we add 1, that'll be 0, 2, 3. Okay. Okay. Okay, so brothers and sisters, we made some more progress though, right? I'm gonna take a look at that again, and cause I don't want to take up no whole other time with that. But that's good that we slowly building on that, right? I might just leave that statement up here, just something for us to be focused on. But we made some tremendous progress. It's the number set, right? We're talking about the number set. Okay. 1 plus 1 is 2. We have to prove that. Now, let's look at this. I think I can just do it without looking. Given a variable t greater than 0, there exists a variable nt in n such that 0 is less than 1 over nt is less than t. That was the analysis problem that we also talked about. And I had a problem. Now, again, let's remember this fundamental principle. When you have 1 in the denominator and you have n in the numerator, and then we say, well, as n goes to infinity, as n gets so large, this 1 over n goes to 0. If you have a calculator and you divide 1 by a number and then increase the number and keep increasing that number, you will see that the number a gradually goes to 0. It never equals 0, but it'll be something like 0.12, and then it'll be like 0.10, and then it'll be like 0.09, and then it'll be like 0.01, then it'll say 0.001, 0.0001, and it'll keep going on and on and on and on and on and on, but it will never equal 0. So when you talk about math analysis, and you're trying to prove, see, again, math analysis is really, it's really not, like, it's not nothing that you can apply to like engineering or physics. But what math analysis does is it reshapes how you think. And because of chattel slavery, I mean, it's just common sense. But again, you know, only those that hear will hear. Moses, in the history of the planet, Moses took tricknology into the caves and hillsides of Europe. The tricknology is mathematics that he took to Europe. And it's not only mathematics, it's math analysis. Let's look at the tricknology, what they call tricknology. The tricknology is that, look, if n goes to infinity, that's a trick already, right? Because you don't even know what that means. But let's just look. If n goes to infinity, well, if you put n in the denominator and you divide that into 1, which is in the numerator, then the value of that variable, of this function, you can call this a function. The value of this statement is 0, but it's only 0 as n goes to infinity. That means that as this n goes to infinity, this value goes to 0, but it never equals 0. That's some hellified tricks in that statement. How if you don't know what that is, you're going to be tricked because you don't know that. That's beautiful. The science, like just how God has it, right? Okay, so let's stay focused. Now, let's look at it like this. you have a number set. Say we got something called a closed number set, and you denote a number set that's closed with these square brackets. You might see it on your computer keyboard. It'll just be square brackets. So then inside of these brackets, we might say A, comma, B. Right? So then you do a number line. And you put 0 on the number line. And then you say, well, you want A and B to be positive numbers. Or better yet, okay, hold on a second. Let's stay with the number line step by step. So you have 0 here, right? You got negative numbers to the left of 0. You have positive numbers to the right of 0. So you're saying you want A to be a positive number. And always understand when you have this is called a closed number set. Whenever you see these symbols right here, that's a set. It could be an interval, but we just want to keep it generalized. This is a set, but it's closed. It's not open. An open set is the parentheses. This is now talking about mathematics. When you use parentheses in this shape, that's an open set. This is a closed set. So we're talking about a closed set. A closed set means that when you're dealing with this set, so you label it, another variable. We label this set S. So when I talk to you, I say S. You don't say, well, I don't know what S is. No, you do know what S is. S is the closed number set with variable A and variable B. We call that S. And what that means is that every number in this set equals A is in between A and equals B. And A is less than B, or A is less than or equal to B, or A is equal to B. Always understand that you can define it however you want. Now, normally it's just understood, right? If you just see it like this, that's understood where A is less than B. Again, understand they got something called, it's called ordered pair or ordered relations. These variables have a relationship. Whenever they get around each other, they have a relationship. And that relationship is A, this is all it is. A is less than B, B is less than A, or A is equal to B. And that's the relationship. This right here is called the trichotomy principle. Trichotomy principle. So when you write a paper, I mean, it's understood, but sometimes, like if you're trying to just show the professor what time it is, like to make sure, cross them T's and dot them I's, you might just throw that in your paper, right? And from the trichotomy principle, right? So listen, look at what it say now. You talk about the relationship. Variables have relationship. Variables have a relationship. And that relationship is that A is less than B, B less than A, or A equal to B. Now, you also have where A could be less than or equal to, A could be greater than or equal to. But that's just finessing what you already know. But again, let's understand. Variables have a relationship. And that relationship, now, again, okay, so I said that kind of incorrectly. When you talk about the number system, all variables have a relationship. But within the number system, we have something called ordered pairs, and that's dealing with space and coordinate systems. So that's going to be like a lot of knowledge to speak on, so we going to keep it simple, right? But when you talk about an ordered pair is what it is. So when you have variables within a closed set, that creates an ordered pair relationship. So A and B in this situation have an ordered pair relationship, and because A and B within this closed set S, because they have an ordered pair relationship, they can only have a relationship where A is less than B, B is less than A, or A is equal to B. That's how that comes about, because understand now, when you talk about the number system, A and T, listen to what we said now. We said T is greater than 0 such that there's an NT in N. So NT has a relationship with the natural number set N. But it's not a less than, greater than, equal than relationship, because these are not ordered pairs. That's just another way to write some separate language when you're trying to communicate a problem. Okay. But if you look at this statement right here, 0 is less than 1 over NT less than T. 1 over NT less than T, they have a relationship. Now, it's not necessarily an ordered pair relationship, but then when you use the less than symbol, it becomes an ordered pair relationship. But again, when I think of ordered pairs, I'm speaking more about spatial coordinates. So that's just going to be a discrepancy a discrepancy in schools of thought. But 1 over NT less than T has a relationship, a variable relationship. Okay, so again, what does a closed set mean? When you have these brackets, square brackets, and you say, well, it's a closed set, and you put variables in the closed set, what does that mean? That means that AB creates an interval. And we're going to say that the relationship between A and B is A less than B. That means that on a number line, you have A and you have B. Now, normally, we would specify that A was greater than 0, but we're just going to keep it moving. But we did specify that A is less than B. So if the number set, if the closed set S is greater than 0, then A and B are to the right of 0. My whole point is this. When you use the square brackets, everything inside of the brackets, everything between A and B, listen now, it's a space, there's some space between A and B, but we're also including A, and we're also including B. And because A is less than B, and because there's some space in between A and B, that means that A is the lowest value and B is the greatest value. And the space in between A and B, you can call that whatever. Let's call it X. So then when you start speaking about NT and N, or 1 over NT, right? Well, it's better, let's look at it like this. When you say NT, NN, you're talking about numbers in the natural number set. So let's say that we're talking about A and B being in the natural number set. So we intuitively know that A is greater than 0. Let's look at it. Let's look at this too, right? These thoughts be coming to me. They be from God. How I want you to understand this. Look at this. when you talk about analysis, right? Let me see something. Okay. When you talk about analysis, and I say, well, look, how can I say that? Say we talking about the natural number set. And I say, well, the natural number set, let me do it like this. There's a number A. We don't know what that number is. We just going to say we're going to call it A because we don't know what it is. There's a number A in the natural number set N. And then I ask you, is A greater than 0? Let's think about this for a quick second. Let's slow it down, get the language correct, get our thoughts correct so we can understand. We thinking about some number. We're going to call that number, because we don't know what it is, it could be whatever number you want it to be. But initially, we don't know what the number is, but we want to use a number. But what number? Well, we don't know what number. So we're just going to call that number A. A variable. It can be whatever number you want it to be, but you first got to understand that if you don't know, if you haven't decided what number you want, let's just call it A until you decide what number you want. And we're going to take that number A and we're going to start putting boundaries on it. We're going to say, well, look, we're going to take this number A, which we don't know, and we're going to put it into the natural number set N. I'm not going to tell you no more or nothing. I'm just going to tell you natural number set. So when I say natural number set, you done already studied. We done already put it on the board. It's very simple. You know what it is, right? You got to know what it is. And that's it. So I'm going to take a letter, I'm going to take a number, we call it A, and I'm going to put that number A into a natural number set. And then I say, well, look, A is less than 0. Or A equals a negative number. How did I want to say that, right? Okay, that's the same thing, right? Okay. So we're going to say, so I say, look, I'm thinking about a number. I'm going to call that number A. I'm going to put that number into the natural number set. And then I'm going to tell you, look, A, or I'm going to ask you, is A less than 0? So think now, I'm asking you, you have a number in the natural number set. And then I ask you, well, is that number less than 0? If A is in the natural number set, is A less than 0? Is A less than 0? Is A equal to 0? If I say equal to 0, that's going to, if I say less than 0, then I ask you equal to 0, that's going to kind of give you the answer, right? But if you see something like that, if you see a letter, a variable in the natural number set, and then someone asks you, is A less than 0? Well, the answer is no. Because there are no negative numbers in the natural number set. So A has to be a positive number, because the first number in the natural number set is 1. And again, that's how analysis works. Oh, that's so powerful. So why do I say that? I say that because whenever you see these two symbols right here, it's a square bracket. And you see some variables inside the square bracket. Right? Normally, if we don't define the relationship between the variables, normally the variable on the left is less than the variable on the right. So it's like an increase. You're going from A, which is at the bottom, to B, which is at the top. Or if you're speaking about a number line, you're going from A, which is less than, B, which is greater than. And if this number set S is in a real number set, then you're talking about an infinity of numbers between A and B unless you prove that A is equal to B. If A is equal to B, regardless of what set it's in, there's nothing in between those two variables. If A is equal to B, that means that A is equal to A. So how can there be a number in between A? So that's the game again. That's analysis. That's trigonometry. But let's stay back focused. So the square brackets mean that when we're speaking about this set, it's a closed set. That means that we're speaking about every number in between A and B, because we're talking about a real number set. But we're also including A. And we're talking about every number again between A and B, but we also including B. But look, we say here A less than B. So that means that the lowest number in this closed set is called a closed set. A closed set, a set of natural numbers, a set of numbers in the number system. So we're talking about a closed set. Okay. So a closed set has a least number, a number of minimum value, and a greatest number, a number of maximum value. There is no number within this closed set that's greater than B. There is no number within this closed set that's less than A. So why do I say that? Let me say it one more time. You have a closed set A, comma B, and we call this closed set S, and we put S in a real number set, and then we come to the number line, and we didn't specify that it was but we specified it here that 0 is less than the closed set, so that means that A is going to be greater than 0. So you have a certain amount of space between A and B, and initially we assume that A is less than B because of how you read this closed set in literature. But then we also define it. We say A less than B. So because S is in a real number set, you have a certain amount of space or density of numbers. But within this set of numbers, it's closed. So what that means is that we're speaking about every number in this set in between A and B and A, and we're also speaking about every number in between A and B, including B. And that's a closed set. Compared to an open set. An open set, you use regular parentheses. So if it's an open set, we say A less than B. The open set means you're speaking about every number between A and B. Well, then we use an open circle. But we're not including A and B. We don't include A and B in our list of numbers, but in a closed set, we include A and B as numbers we can work from. Okay, so let's understand. That was a lot, right? I say that because, again, when you have a closed set, A, B, the least value in a closed set, AB is A. There is no number less than A in this set, And there is no number greater than B in this set. So look, right? If we say n goes to infinity, and then we say 1 over n goes to 0, as n goes to infinity, 1 over n goes to 0, right? So then, how do we want to say it? Okay. We have nt in a natural number set, right? Now, what I want to say is that I think the last lecture we had some type of confusion with n and nt, so when doing a little research, when you have nt is like a sequence of numbers compared to n, which is like a number that the sequence converges to. Like every number, so you got n1, n2, n3, and all of these numbers are converging to n. That's still confusing, right? That's still confusing. Okay. But the whole point is this. Let me just look at the book to make sure, right? Because I think we still going to have that problem, right, where I disagree. It's not that I disagree, right? It's just, it's your understanding of how the, what is it? Schools of thought. It's just a separate school of thought. Okay. Okay, so they put n, look now, they put n in the natural number set. We already know nt to be in a natural number set. So if n is in the natural number set, and if nt is in the natural number set, the understanding is that nt goes to n. That's kind of still confusing, right? But we're going to see if it makes sense. But we have n in the natural number set. You have nt in the natural number set. But when you're just speaking about n, they're saying the infimum, look at it now. Infimum, infimum. And we said that the infimum is the greatest lower number. Greatest lower number. So I put closed, remember now, I put the closed set, and I said A, B. Now, the infimum of this right here is what? If we're talking about the greatest lowest number, first of all, in this closed set AB with A less than B, what's the least number or the lowest number? What's the lowest number in this closed set? Well, because it's a closed set, we include the numbers in between A and B because A is less than B, but we also include A. So the lowest number in this closed set is A because it's closed. Now, if it was an open A, an open bracket, or open parentheses AB, this would not be true. We would have to find that. But because it's closed, the symbol square brackets lets us know that, well, they're just going to give you what the least number is. So the least value in this closed bracket is A, and the greatest value in this closed set is B. So an infimum is the greatest lower number. Then you have something called a lower bound. Lower bound. So you got numbers that's less than A. If you go back to the number line, you say from A to B, we including A and including B, but you still got numbers all right here that are lower than A or less than A. That's called the lower bound. We're not talking about the numbers that are not in the set. We're talking about the greatest lower number. So how they define that, the greatest lower number is in the set, which is A. You have a number that's right after A, but that's not the greatest lower number from the lower bound. I got to explain that too, right? That's a lot of explaining. Okay, but we're making progress. We're making progress. Okay. So they put n in the natural number set. And then they say, well, 1 over n, right? But we got n going to infinity. So if n, okay, so look now, because it goes to infinity, because it's in the natural number set. Natural number set goes on to infinity. So we're not saying 1 in the natural number set. 1 doesn't go to infinity. 1 goes to 1, or 1 is 1. But we're saying n, that represents an unknown number. We don't know what it is. So it goes to infinity. So as n goes to infinity, we have a structure, a mathematical structure, where if we say 1 over n, and if we have n go to infinity, then 1 over n goes to 0. It never equals 0, but it goes to 0. So look at this, right? This is what they're saying, right? They're saying that because 0 is not, when you have a natural number set, 0 is not in that set. Because 0 is not in that set, and the lowest bound is 1. How you doing? You have a class here coming up?
In about like 40 minutes.
Okay, could you give me about 10? Yes, sir. Just 15 minutes. I appreciate it. No, sir. So, if the natural number set, if the lowest bound in the natural number set is 1, but now they're saying that the infimum, or the lowest bound, the greatest lower bound is 0, then NT, because NT converges to 1 over n, and since 1 over n is equal to 0, they say 1 over NT is equal to 1 over n, which is equal to 0, but we have t greater than 0. So therefore, 1 over nt is less than t. And that's what it is, brothers and sisters. Now, again, it's not right and exact as far as the literature, so we have to, again, look at that to see if we can further understand what's going on. Okay. Okay. So we probably got about another 10, 15 minutes. So now it's like it's so much information. Like, what do we want to speak about? Right? And I got references that I want to give to you. So let me put this on the board again. It's called ResearchGate. ResearchGate.com. You should really get on researchgate.com. And again, if you're a college student, use your your student identification to join real good, let people know you in college and you trying to network. It's just the researchgate.com is just a network of doctors and students that are just doing research, and you can get all types of what's going on. Whatever you want to speak about. Researchgate.com. Okay, I pulled something. We're going to talk about ballistics. Again, ballistics. And I did want to speak about the brother Armand, but I don't think I'm going to have enough time, right, to speak on him, to just get everything in context, right? But we're talking about ballistics, right? And so I pulled a couple journals. They had some nice information on there. So let's see if I can just go to the journals and get like a quick overview. I seen one that gave a couple diagrams. It talked about the chamber of the pistol. Now they're talking about the trigger mechanism they're talking about using the trigger mechanism underwater. So let me see something. Bismillah. Okay, now this is going to be from my brother. Where they from? Okay, they might be from Cambodia, just in how they spell their name. I can't be for sure, but it looks like Cambodia. It's either Cambodia or Vietnam, but I'm gonna say this is Cambodia. But let me give you the title of the journal article. It's called Dynamic Analysis of Firing Mechanism of an Underwater Pistol. Now they wrote this in English, so again, right, to actually get that knowledge in their language. But the title of this journal article, and we're going to study this, we're going to put some time into, if it makes sense for us, see if we can really look at what they're speaking on. But they give you a diagram, just initially looking at it. They give you a figure, they call it figure 1, and they have 2 scuba divers underwater with some type of handheld pistol. And it says figure 1, 2 kinds of typical underwater pistols, HK P11 underwater pistol and a SPP 1M underwater pistol. Now again, they got us underwater talking about a gun, right? So I'm not saying that's crazy. I'm just saying, right, am I just looking on the internet on researchgate.com? This is what made sense. And we're still looking because we're just trying to get that one paper. I mean, it's in there. I just have to find it. But this is also good because now you're talking about something underwater, right? That water going to slow that motion. I mean, the brothers ain't dumb now. So if it's going to slow that motion down, you're thinking about that, right? So that means you can think about how slow that trigger pulling. So it's, it's just how we communicate, right? But in that environment of an underwater trigger, shooting a gun underwater, it better helps you visualize how to connect to get everything moving. So let me read it to you one more time. The name of the journal article is Dynamic Analysis of Firing Mechanism of Underwater Pistol. So the dynamic analysis, again, look at that word, analysis, they letting you know they're getting this from math analysis. So we're going to analyze this trigger mechanism. The trigger mechanism. Seek ye first the kingdom of God and all of his righteousness. Then we're going to look at the trigger mechanism, right? If you can take the metal out of the earth, you can shape it and mold it however you want. But that bullet will just sit in some type of square if you ain't got that trigger mechanism. So we got to master how to make the mechanism, or just mastery of how it works. Like in your mind, you just know how it works. And you can just write on a piece of paper. Okay. Dynamic analysis of the firing mechanism of the underwater pistol. Let's just read a little bit of what, okay, this is from my brother Dung and Julian Thai and Hung and Julian Vaughn. Some powerful names, right? This is the abstract. The important problem of designing an underwater pistol was analyzed and calculated. The dynamics of the firing mechanism. I would just say, brother, why would we even want to be, okay, we would want to be underwater shooting a gun to better understand the physics of why the bullet travels out of the gun at what type of speed, right? So it's, again, it's the mindset. We're in a devil society, right? So it's a total separate mindset. On the basis of analyzing the performance of the underwater pistol, the paper presents a theoretical model. And I'm gonna tell you like this too, right? When you talk about, like, if you're underwater, you know, water is like a brick wall if you're just standing still. So if you're gonna shoot a bullet through some water, that's like shooting a bullet through some steel. So that means you got to have a certain amount of force, and that goes back to like the creating of the bullet, right? And what type of gunpowder, what they call it, smokeless powder, what type of powder you're going to use to create that explosion where it'll have enough force. What's the force? What is it? I think forces per meter per second squared. So now you have to create, because the whole thing, like, look, you underwater, you shoot a bullet. Listen, if that bullet come out 100, if that bullet come out, say the bullet come out like 3 inches per hour, then when it come out, it'll float. Oh, look, right? Say if you got a gun underwater, say if you underwater, right? And you got a gun, and you create a force that's so powerful, and that impact make that bullet come out the gun, but when it hit the water, it just started floating. You see what I'm saying? So that's like the physics. And once you understand all of that, again, the trigger mechanism becomes very simple. And we get all of this from God. And God tell us math analysis from 400 years of slavery. Okay, let me read a couple more sentences. On the basis of analyzing the performance of the underwater pistol, the paper presents a theoretical model for analyzing the dynamics of the firing mechanism of an underwater pistol with the resistance of water force acting on the firing pin and slide. Okay, they got real deep with it. They're not talking about the force right here. They're saying how the force of the water affects the, oh, that's real good. Because the firing pin and the slide, the slide is the entirety of the gun, but I'm thinking the firing pin, right? So they're looking at all of this. So again, my brother name is Dung and Julian Ta and Hung and Julian Vaughn, and we might actually set aside some time where I might start teaching from this journal. Now I'm not going to be all on it, right? Because we still want to prove our path. But so far it sounds good, right? And what I will do is that if I look at the journal, and if it's something that's actually very good, they already got what we're looking for initially, even though we're underwater. I'm gonna put it on my internet site. If you go to www.fatihaduasharia.com, and then if you go to a law school of mathematics, a law school of mathematics, Mathematics. Go to the Law School of Mathematics, and I have some categories. And I think, well, one of the categories is publications. If you go there, I'm gonna try to make that available if I like it, and you can just download it from there, and you can take a look at it. But again, ResearchGate, I took it off, but ResearchGate, they are just one of many, but ResearchGate is very good if you're trying to become fluent in some type of discipline. Audu, Bilaye,